Welcome to this particular course. You already have seen the introduction part where I am talking about what is the importance of this particular course, what you will be learning in this course, how it will be helpful for you to use the knowledge from this particular course in the actual research domain, as well as for understanding the various sensing principle of sensors and actuators. Now let us start with the first class of this particular course, and let us understand what are the sensors and actuators, and what exactly a sensor is and what is the actuator. Right. So, any tool and component that is within the machine that is responsible for the physical movement of the other parts or for actuating it is an actuator. Okay. While when you talk about sensor, sensor is when it senses the physical or the optical physical parameters. For example, let us talk about temperature. If you can measure the temperature, it is a temperature sensor, right. So, a sensor and actuator, there is a fundamental difference in the way both the components are defined. When you talk about actuator, you can take an example of a valve. When you talk about sensor, you can take example of accelerometer, temperature sensor, gas sensor, right. Now, what kind of sensors are there? Are there direct sensors, are there indirect sensors, right? What is the principle behind these sensors? So, today we will focus on what kind of sensors are there and what are the mechanism and principle that sensor depends on. Let us see the slide. When and in particular we will also focus on micro and nano. So, the idea is not just to tell you about the sensor and its mechanism or actuators and its mechanism or as well as application, but also to make you understand how you can design sensors or actuators and or actuators which are micro in dimensions, and sometimes you use the nano material to fabricate or realize the sensors. So, when you talk about micro, what micro means? Micro means 1 millionth, right. So, if you talk about human hair, it is about 80 to 100 microns. Now, you are talking about 1 micron. 1 micron would be about 10 to the power minus 6. Alright. So, you can see on the right side of this slide, starting from meter, right, we have 1 meter, then you have 10 centimeters, then you have 1 centimeter, 1 millimeter, 100 microns, 10 microns, 1 micron, then you have angstroms and then 100 angstroms, right, 1000 angstrom, 100 angstrom, and then you go to 1 nanometer. So, what we will be talking about is in this particular range from micro to nano, alright. And then we will see why it is very important to design sensors which are of micro dimensions and same way for the actuators as well. Okay. Now, nano, like what I was discussing, is about 10 to the power minus 9, or you can say it is 1, meaning 1 billionth, alright. 1 by 1 billion will give you nano, which is 10 to the power minus 9, right. You can see that 33639, where if you talk about million is 1 by 1 millionth, which is 3 and 3 6. So, it will be 10 to the power minus 6, this will be 10 to the power minus 9, right. Okay. That stands for your micro and nano. Now, when you talk about molecular manufacture, it is like precision down to the atomic level. You have several systems which can help you to deposit the layer atom by atom. So, molecular manufacturing stands about depositing the precision down to atomic level. Nanotubes were building advanced lightweight materials as an advancement in LCD technologies. There are a lot of advancement here. You can see that from the CRT to the LCD that we use today, that is a huge improvement, particularly because of the lightweight materials and advanced technologies. Same way when you talk about medicine, there are devices that will flow through the circulatory system. They are all micro and nano devices. Lot of research is going on in this particular domain as well. When we talk about nano composites, is about assisting in various improvements in material composition, while when you talk about electronics, we are talking about advanced complementary metal oxide semiconductor and silicon transistor indicated with lithography or indication with lithography. So, when you talk about just sensors and actuators, it does not mean that you are just talking about the phenomenon or mechanism. You are also understanding how you are going to fabricate those sensors, and that is the goal of this particular lecture as well as the course, is to show it to you what kind of sensors are there, but also to explain you how can you fabricate those sensors. When I talk about fabrication, there are several techniques that you will be learning during this particular 30 hours course, and then we will see that when you talk about lithography, like we just discussed in the first slide, that when you want to design an electronics, for example the complementary metal oxide semiconductor, or you want to design the sensors or silicon transistors, then you need to rely on the lithography. So, we will be discussing about lithography, we will be discussing about the systems, and then we will see how you can design using the micro technology processes different sensors and actuators. Right. Now, when we discuss about this, you should understand that we are not only going to discuss about this, but we will be looking at how the sensors looks like. For example, if I show you a sensor right in my hand, you can see the sensor. Right. So, this is a sensor that we will be talking about. Now, these sensors are from Taguchi, it is a Japanese company, but what we want to understand is what is there within this particular sensor, within the casing, right, and what is the role of having x number of pins below the casing, what is sensing material that this particular sensor is using, and finally can we fabricate this sensor. Right. So, the answer is yes, we can fabricate the sensor, and I will show it to you how to fabricate the sensor and how to make the casing. This is one just giving one example of the sensor. We will show several examples. I will show it to you several examples of different kind of sensors. Let me show you one more sensor. Actually, few I have. I will show you few of the sensors. This is another sensor that I am holding in my hand, and these are all gas sensors. Okay, these are all gas sensors. This is a pin on the back side, and the front side you have the mesh through which the gas can pass, and then within it is a sensing layer. When a particular amount of gas is passed, there is a change in the resistance value. I will tell you why there is a resistance initially and how the resistance value changes when a particular gas comes into contact with the sensing layer. Alright. So, we are talking about the another sensor that I am holding here, which is again a gas sensor, and then in gas sensor when I talk about, there are VOC sensor as well. So, what do you understand by VOC? VOC stands for volatile organic compound. Okay. Now, when you say volatile and then you say organic compound, so can you think of some volatile organic compounds? It is very simple. If you think of volatile organic compounds, you will see that petrol, right. So, when you put a drop of petrol is there, it will immediately evaporate, right, at room temperature. Same thing when you talk about acetone, can you please see on my hand the sensor that I am holding. So, when you talk about acetone, right, acetone is again a volatile organic compound. When you talk about ethanol, is a volatile organic compound. When you talk about methanol, is again a volatile organic compound. When you talk about IPA, isopropyl alcohol, is again volatile organic compound. When you talk about butanol, is again volatile organic compounds. There are list of volatile organic compounds. Okay. So, the sensors that I am showing it to you is not only a gas sensor, but it is also a VOC sensor, volatile organic compound, VOC. Right. Now, you will ask that what is the use of this particular sensor, why to measure VOCs, right. So, there are a lot of applications of VOCs. alright. One is ethanol sensor, for example drunk and drive, right, drinking and driving is not good. First of all you should try to avoid drinking, but at least if you are drunk you should not drive, very simple. The point is it is injurious to your health, alcohol as well as smoking, and you all know, I am just telling you once again, the idea is to make you understand that if you want to know what is the blood glucose concentration, then you can measure the amount of ethanol from the breath using ethanol sensor, right. So, this sensor can be used as an ethanol sensor. Ethanol is volatile organic compound, right. So, this is again a VOC, right. Refrain yourself from having any kind of bad influence, bad habit. Like I said, sensors and actuators we are learning, but we can learn everything only when our sensors and actuators are working well, right. See, we have eyes optical sensor, we have acoustic sensor, we have a sound vocal sensor, right, we have taste buds, we have force sensor, we have touch sensor, right, everything is sensors. And this will get deteriorated over a period of time if you keep on having bad habits such as drinking a lot of alcohol or smoking tobacco, it is not good. So, try to be away from such kind of habits, but at the same time you should know that what is the effect when somebody drinks alcohol, how it is converted or mixes with the blood, and how it comes to the breath, so that a person can be identified under the influence of alcohol through the breath, right, by using alcohol sensor, and alcohol sensor is nothing but a ethanol sensor, right. So, this is another sensor that I am holding in my hand, and you can see there are 4 pins in the bottom. What is the role of these 4 pins at the bottom? I will teach you in some other class. This is another sensor that I am holding. These all sensors are from Taguchi, alright. Now, there are CO2 sensors, there are ethanol sensors, there are methanol sensors, there is a humidity sensor, okay. So, lot of sensors are there. Some sensors comes with electronics embedded, some sensor does not come with electronics. Now, this is a sensor that comes with electronics right in the back side, as you can see here, alright. Front side is your sensor, back side is your electronics. So, how to use it? You have to just there are pins to connect the sensors, and you can immediately use it for measuring a particular gas, right. So, let us first understand before. So, this is just like I am giving some examples that these are all gas sensors, but the sensors are of several types, from, like I said, from temperature sensor, accelerometer, light sensor, magnetic field sensor, we have photo gate, we have CO2 gas sensor, we have ultrasonic sensor, and so on and so forth. Okay. So, let us understand today sensors, and then like I said we will continue with the actuators. So, if you see the slides, our focus of this particular lecture is to understand what are sensors, then we will look at what is the detectable phenomena or what is the mechanism, physical principles, that is how do sensor works, need for sensors, choosing a sensor, what kind of application you are targeting and what kind of sensors you have to choose for that application, and then we will see few sensors and their applications, from temperature sensor to CO2 gas sensor, alright. So, when you talk about sensors, so the American National Standard Institute definition is a device which provides a usable output in response to a specific measurement, right. So, a sensor is nothing but a device that can give us an output for measuring a particular measurement, right. So, in response to a specific measurement. That means that a sensor acquires a physical parameter and converts into a signal suitable for processing. For example, light, then optics. So, can I see the intensity of this particular light and convert it to a phenomenon or to a output signal that can be useful. For example, can I convert this light to resistance, right. So, all light to current, light to voltage, whatever, doesn't matter, some measurable output. What is the measurement here? The light intensity, right. So, it can be optical, it can be electrical, it can be mechanical. Suppose this is a cantilever, assume that what is cantilever? I will give you example of a cantilever. You have seen diving board is in a swimming pool, right. So, the diving board on which a person stands and dives, right. So, that itself is a cantilever. It is holded from one side like this, right. So, when you press it, it bends like this. So, every cantilever is operating at its natural frequency or vibrating at natural frequency. Now, if you consider this as a cantilever, if I press this cantilever and if there is a piezoresistor embedded into this cantilever, what will happen? When I press it, there is a change in resistance. Why there is change in resistance? Because piezoresistivity is a phenomena. Why? When you apply a pressure, there is a change in resistance, right. So, if there is a embedded resistor, piezoresistor into this particular cantilever, assuming that the pen that I am holding is a cantilever, the piezoresistor is right over here. When I apply a force, because of the strain, there is a change in the resistance. So, now the force that I am applying is the signal, is the measurand, and the resistance that I am looking at is the output. Is if my output is in the detectable range, right, or usable range, then I can say that this cantilever is nothing but a sensor. Okay. That is just giving an example. So, a sensor, like I said, acquires a physical parameters and convert into signals suitable for processing. While when you talk about transducer, and transducer is like microphone, loudspeaker, biological senses, example touch, sight, etc. So, transducer transduce the signal, for example loudspeaker, like whatever we speak, it amplifies the signal, right. So, that is the transducer. When you say about detectable phenomenon, that means that what is a stimulus and what is a quantity. For example, if we talk about acoustic stimulus, then we can have wave, there is amplitude, phase, polarization, spectrum, wave velocity. When you talk about biological and chemical kind of stimulus, then what is our quantity? Fluid concentration such as gas or liquid. So, when you talk about electric, then what is the quantity? Charge, voltage, current, electric field, amplitude, phase, polarization, as well as conductivity and permittivity. When you talk about magnetic, then you have magnetic field, which is amplitude, phase, polarization, as well as flux and permittivity. While optical, the quantity is refractive index, reflectivity and absorption. For thermal, it is temperature, flux, specific heat and thermal conductivity, while for mechanical it is position, velocity, acceleration, strain, stress, pressure, force, torque, right. So, this is how the stimulus and the quantity can be defined. Now, let us see physical principles and then we see need for sensors. When you talk about physical principles, there are several laws that we need to understand. First law is Ampere's law, where a current carrying conductor in a magnetic field experiences a force, for example galvanometer, right. While when we talk about Curie-Weiss law, then there is a transition temperature at which ferromagnetic materials exhibit a paramagnetic behavior. There is a Curie-Weiss law that at a particular temperature, which is a transistor temperature, your ferromagnetic materials will behave or exhibit paramagnetic behavior. While when you talk about Faraday's law of induction, most of you should know it is a coil resist a change in a magnetic field by generating an opposing voltage or current, right. For example, a transformer are several types, we know there is a step up transformer, step down transformer, right, and then each of them has its own core. So, that it comes in the transformer section, we are not focusing on that, but I am just giving an example that the Faraday's law of induction works for transformer. Then we talk about photoconductivity effect. So, photoconductivity effect is when the light strikes the certain semiconductor materials, the resistance of the material decreases. For example, a photoresistor. So, what we have to understand is that every or most of the sensor they operate on certain principle, either it can be Ampere's law, it can be Curie-Weiss law, it can be Faraday's law, it can be photoconductivity effect and so on and so forth, alright. So, if you see the slide, these are the physical principle, like I said, Ampere's law, Curie-Weiss law, Faraday's law of induction and photoconductive effect. Now, when you talk about need for sensors, what is a need? So, the need for sensors is sensors are omnipresent, they embedded in our bodies, automobiles, aeroplanes, cellular telephones, radios, chemical plants, industry plants and countless other applications. I told you sensors are everywhere. You talk about your body is full of sensors, right. I just give you few examples. We have a temperature sensor, we have optical sensor, we have a touch sensor, we have force sensor, we have tactile feedback, right. And then we have acoustic sensor, we have transducer, right. We have amplifier. How like amplifier, I can increase the amplitude of my signal, right, and decrease it based on how I want to deliver my lecture, right. So, you are full of, or a human body is full of plenty of sensors, and that is how we try to mimic some of the sensors in real time. Whatever we feel, for example force, like if I am holding a pen, I know how much force I have to apply, I can get a feedback as how much force I am applying, right. Tactile feedback, I also can have haptic feedback. So, without sensors, you see that there can be no automation. For example, see all the aeroplanes, if you see flight, when you take a flight or you go, you sit in a bus or travel in a auto rickshaw or travel in a car or travel in a train, yeah, or even your motor bicycle, everywhere there are sensors, okay. And the importance of these sensors are tremendous. Okay. So, for example, let me give you a very simple example which we can correlate with our daily activities. If you see you may have used milk in a package, right, but the milk that goes to a package or packaging of that particular 1 liter or half liter of milk occurs through an automation system where there are a lot of sensors involved. Can you imagine to serve milk in terms of like package milk to this many people if the phenomena or if the process is done manually? It will take hours, right. Now, because of the automation, because of the sensors, this time is reduced tremendously. This is just given an example of sensors in our real life, packaging of milk for example, right. You can correlate with several examples. So, without the use of sensors there will be no automation. Now, let us understand choosing a sensor. Okay. So, environmental factors is one of the thing that we need to understand. We have to understand economic factors and then we have to see what are the sensor characteristics. So, if we talk about environmental factors, then what are the factors that we have to consider? For example, what is the temperature range, how the humidity will affect the sensor, what kind of corrosion is there, what is size of the measurement, overall overrange protection, susceptibility to electromagnetic interference, that is called EM interference, ruggedness, how rugged your device is, power consumption, is the device capable or sensor capable of using less amount of power. So, power consumption is very important phenomenon. Then your self test capability, repeatability, right, lot of things are there which you call about in environmental factors. But when you talk about economic factors, you know that it should be low cost device, it should be available, the lifetime should be extremely high. Suppose I get a sensor to measure the temperature in my home, right. Now, the lifetime of this temperature sensor or the system is just 1 year and the cost is like 50k, then I cannot buy it, right, because the lifetime is extremely small. But if I say that it will be lifetime warranty, right. So, assuming that average human life is about 70 years, then 70 years the sensor will work, right, for 50k, then it can be one can give a thought about that. However, if you say that for instead of 50,000 I give it to you for 5,000 and give you lifetime warranty, then you will immediately buy it, right. So, the economic factors are very important. The when you make a technology can be while devising the technology you have to invest a lot of money, but once the technology is ready it should be at a lower cost, except that it is specialized technology. Okay. So, cost, availability and lifetime, these are economic factors. When you talk about sensor characteristics, what are the sensor characteristics? It can be sensitivity, can be range, it can be specificity, it can be stability, it can be repeatability, it can be frequency response, it can be response time, it can be error, it can be linearity. So, several sensor characteristics are there that we need to take care when we design a sensor. How linear my sensor is, that means that with increased suppose temperature sensor, with increased temperature, if my output is in terms of resistance, is my output linearly decreasing or increasing? Then I can correlate that for 1 degree change I will have 10 degree or 10 ohm resistance change, for example. If it is a linear, it becomes easier for you to design the signal conditioning systems, right. So, linearity extreme. How sensitive it is, for 0.1 degree can I see the change? Sensitivity. How specific is it is, right. How repeatable it is, right. It goes to 34, it comes back to 25, again goes to 34, again comes to 25, how well it follows the curve, right. How stable it is, if the room temperature is 24, is my resistance stable? Stability, right. What are the errors, right. When I go from 24 to 30, back to 24, back to 30, back to 24, what kind of errors I have in terms of resistance? Am I getting the same resistance every time when I reach 24 degrees centigrade? Am I looking at the change in resistance every time when I reach 30 degrees centigrade? What is the error, or what are the errors? That is another point that you have to understand, right. Response time, how fast it changes, right. A 0.1 degree change, suddenly can I see the change in resistance? How much time? Is it milliseconds, few seconds, few minutes, right. It is microseconds, how fast it is? Response time, right. So, these are some sensor characteristics, alright guys. So, when you talk about choosing a sensor, you have to take into account all 3 parameters: environmental factors, economic factors and sensor characteristics, 3 things. Okay, cool. So, now let us see the first sensor, which is our accelerometer. If you see on the slide, accelerometer are used to measure along one axis and is insensitive to orthogonal directions. The application of accelerometers are in vibrations, blast, impact, shock waves, in airbags, washing machines, heart monitors, car alarms, right. So, this is just an equivalent circuit of the accelerometer. You can get accelerometer ready made, and you can measure the vibrations. Like I said, it is placed in the airbags in your car, it is there in the washing machines, it is there in the heart monitors, and it is also there in the car alarms. When you see that, suddenly if you have seen certain places, if there is a car and if somebody tries to open the lock of the door of the car, suddenly there is a alarm, right. So, that alarm also sometimes includes the accelerometer. Your airbag in the car, airbag in any system, right, when there is an impact, the airbag comes out, accelerometer, right. So, blast, impacts, vibration, accelerometer is used. Cool. So, accelerometer we have seen. Now, let us see light sensor. So, light sensors are used in cameras. In particular, we are talking about infrared detectors and ambient lighting applications, alright. So, that is the application of light sensor. Sensor is composed of photoconductor such as photoresistor, photodiode or phototransistor. Now, let me explain you. This is there can be many ways of designing a photodiode. For example, if I want to design a photodiode and if I take a P and N junction, okay. P N junction is what? P is your semiconductor, N type is another semiconductor, right. In P type you have holes as a majority carrier, in N type you have electrons as majority carrier. Now, if I apply a negative bias to my P type and positive to N type, minus to P type, positive to N type, what will happen? The depletion layer will increase, the depletion layer will increase, right. So, when I have depletion layer increased, and if I externally, if I incident a light, what will happen? The electrons will be donated and this depletion layer will start decreasing, right. What I am saying, let us understand again. So, if I have a p-n kind of semiconductor, right, p-n kind of semiconductor, what will happen that when I apply a negative to p and positive to n, then there will be a depletion layer, right. When there is a depletion layer, if I incident an external light onto this depletion layer. So, what is this one? What kind of biasing is this? This is a reverse bias, right. You all know this reverse bias, right. What is forward bias? Forward bias, if I want to see forward bias, what will I do? I have to apply positive to p and negative to n, it becomes forward bias, but I had to create a depletion layer, that is why I am applying negative to p and positive to n. When I do that, there is a creation of depletion layer, right, depletion layer, and when I incident a light onto this particular depletion layer, what will happen? The depletion layer will be reduced because of the electrons formed, because of the intensity of light, and then what will happen? The reduction in this depletion layer can be measured with the help of the current flowing through this particular semiconductor. Thus, this is the phenomenon of any photodiode or a photoresistor or a detector. Okay. So, that is what it is. Now, when you talk about temperature sensors, then you see the temperature sensors appears in several applications, including chemical process plants, engine applications, computers, and many other devices that require temperature monitoring. Many physical phenomena depend on temperature. So, we can often measure temperature indirectly by measuring pressure. We can measure temperature by indirectly measuring volume. We can measure temperature by indirectly measuring electrical resistance as well as strain. Right. Now, you talk about chemical plants, they require to be at certain operating temperature. Engines, if it gets too much heated, it is not correct. Computers, we require to keep it active at a certain temperature. If it is too much heated, the electronics will be destroyed or deteriorated, and same way many other applications. When we talk about magnetic field sensors, then magnetic field sensors are used for power steering. It can be used for security and current measurements on transmission lines, and the way magnetic sensor works is based on the Hall voltage, which is proportional to the magnetic field, right. So, where I have given you an equation, right. So, this is the equation on which the Hall voltage can be measured. When you talk about ultrasonic sensor, then ultrasonic sensors are used for position measurements. Sound waves emitted are in the range of 2 to 13 megahertz. Sound navigation and ranging, which is on sonar, and radio detection and ranging, which is radar, right, both are electromagnetic waves, and there is a use of the ultrasonic sensor in this kind of application. When you talk about another sensor, which is your photo gate, then photo gates are used in counting applications, example finding period of a motion, and also it can be used for infrared transmitter and receiver at opposite end of the sensors. The time at which the light is broken is also recorded with the help of photo gate. Now, when you talk about CO2 gas sensors, CO2 gas sensors measures gases, the CO2 level in environment. It measures in the level in the range from 0 to 5000 ppm. Monitors how much infrared radiation is absorbed by CO2 molecules. For example, if it is infrared sensor, if I have a source and if I have IR detector, then depending on the molecules of CO2, the source and the detector, the signal that is sent from the source and signal that is received by detector would depend on the number of CO2 molecules in between, because that CO2 molecules or those CO2 molecules will be absorbed by the infrared radiation. Okay. So, that is one way of measuring CO2 sensor, but there are several other ways that we will be discussing in the next module. For this module, let us see the two more slides. Now, when you talk about these sensors, right, let us quickly understand that what is a response if the response is an electrical signal. What do you mean by that? So, if you see the slide, the response is an electrical signal. That means that when we say that electrical, we mean a signal which can be channeled, amplified and modified by electronic devices. For example, voltage, for example current, for example charge. Now, the voltage, current or charge may be described by amplitude, right, amplitude. This is the amplitude of positive wave, negative cycle, amplitude, total amplitude, right. Now, it depends on frequency, this is time, this is voltage, right, time in seconds. Let us say if I increase, the frequency is higher, right. It depends on phase, this is, let us say this is 0 degree, then if I have signal, this is 180 degree phase, right, depends on digital code. So, it not only depends on the amplitude, frequency, phase, but also depends on the digital code of the signal. Any sensor is an energy converter. We have seen that this conversion can be direct, or it may be may require transducers. For example, if you have a stimulus E1 can be transducer 1, then we get E2, then you have transducer 2, you get E3, then you have direct sensor, and then finally you have a electrical signal. So, for example, if you want to understand a sensor as an energy converter, a chemical sensor may have a part which converts the energy of chemical reaction into heat, that is a transducer, right, and another part a thermopile which converts heat into electrical signal. Thus the sensor works. So, it can be multiple transducer embedded into one particular block. Now, when you talk about physical principles of sensing and sensor types, then there are several physical principles that you need to take care of, and this is the last slide of our lecture, this particular module. So, physical principle of sensing and sensor types are charges, field and potentials. There can be capacitance, it depends on magnetism, induction, resistance, piezoelectric effect. It also depends on, like we have seen earlier, Seebeck effect and Peltier effects, thermal properties of materials, heat transfer, light, right. Seebeck effect you can just see, go back and check. So, everything that I am talking about, you please go back and understand what is capacitance, what is magnetism, what is inductance, what is resistance. For example, let us just give you one example, resistance, right. How you will define resistance, right, R equals to what, right. It is a you can say that it will resist the flow of current, but it depends how it is depending on the material. For example, if you say a resistance R equals to rho L by A, it depends on the area, it depends on the length, it depends on the resistivity of the material. If the length is higher, resistance is higher. If the area is smaller, resistance is higher. If the area is larger, resistance is smaller. If the length is smaller, resistance is smaller. Several things, right. The resistivity is higher, resistance is higher. Resistivity is smaller, resistance is smaller. So many things. Just we have example of a resistance. Same thing you can understand the effect of piezoelectric. Piezoelectric is what? See, there is a difference between piezoresistive and piezoelectric. Piezoresistive is when we apply a pressure, there is a change in resistance. Piezoelectric is when you apply a pressure, there is change in voltage, right. Crystals, piezoelectric crystals are there. Piezoresistive materials can be designed by doping polysilicon with boron. There can be design we can design a piezo resistor. Thermal properties of material you to understand, you understand heat transfer properties of material, you understand how the light will work, how do you understand C, capacitance, how capacitance is related. For example, I just give you an example of resistance. How about capacitance? For capacitance, the formula is C equals to, if you see the slide, C equals to K A epsilon naught upon D, right. Permittivity, area, constant K, D is your distance between two plates. What is capacitor? Capacitor is nothing but two conducting plates separated by dielectric material or air. What are these two things? These are two conducting plates, correct. Now, the distance between these two plates, the area that capacitor covers, the permittivity and constant, this everything depends on everything defines the capacitance, all right. Now, when you talk about types of sensor types, there are two types, one is direct sensor and second is a indirect or is an indirect sensor. A sensor that convert a non-electrical stimulus into electrical signal with intermediate stages, for example thermocouple, that is temperature to voltage, is a direct sensor. When you talk about indirect sensor is nothing but a sensor that multiple conversion steps or requires multiple conversion steps to transform the measured signals into electrical signals. For example, a fiber optic displacement sensor, where first is a current, then converts to photons, again converts to current, right. So, these are the two examples of sensors, and let us learn the types of actuators in the next class, in the next module. What we have learned here is what are the kind of sensors available, with quick application of sensors, what are the physical principle, when you select sensor what kind of environmental parameters you have to consider, economic factors you have to consider, sensor characteristics that you have to consider, right. And what are the it can be divided into two parts, direct sensors and indirect sensors. In the next class, let us understand how the actuator works. Alright. If you have any question, always remember that we have NPTEL forum through which you can connect to me through my teaching assistants, and whenever you have any question, feel free to ask me through the forum, right, and we will try to get back to you as soon as we can. Please focus on this kind of lectures. When you attend all the lectures with a little bit of focus, you will be understanding lot of things, because understanding sensors is a very important topic, since it can not only be used to understand the several physics principle in physics, but also to understand lot of research problems. So, if you talk about all the medical devices or most of the medical devices, several of those devices they use lot of sensors, lot of actuators. Alright. So, understanding this particular course in detail will help you out with understanding of lot of tools, as well as to come out with an interesting problems in the area of research and development. Alright. So, I will see you in the next class. Till then, you take care, have fun.